Hi, this is Dr. Poonam Upadhyay, Professor in Department of EEE. Electrical circuit is a vast course and three-phase circuit is one of it. And today's my topic I have taken for analysis of unbalanced three-phase circuit. So, analysis of three-phase circuits are basically done by two ways. One is three-phase four-wire circuit where we don't have much problem because we have here, suppose this is my voltage VR. If I take this as R phase, if I take this as Y phase, and this if I take this as B phase, and this is my load ZR, this is my load ZY, and this is my load ZB. So if I connect neutral of the supply to the neutral of the load, when these two nodes are connected, this N and N dash is connected, then I get the balanced voltage supply across ZR, that is VRN, across ZY, that is VYN, and across ZB as VBN. So I get the balanced voltages across this. So it is easy to find out the current, line current IR, line current IY, and line current IB. We can apply the KCL at node N dash and we can get the neutral current also from this method. This method is very popular and it is like known in the in all the books it is available. Next is when we have three-wire circuit and I have here my unbalanced load. So when I have unbalanced load, again I will take here ZR, ZY and ZB. These voltages are VRN. I'll take this as node capital N and I'll take this as node small n. VRN, this is my VYN and this is my VBN. So in three-phase three-wire circuit, the neutral of the supply and neutral of the load, they will not be at the same potential. So I cannot take the privileges what I have taken earlier, like taking the voltages as VRN, VYN, VBN across the loads ZR, ZY and ZB. I cannot take like this because they will not be at the same phase voltages. Though their line voltages will be same, right? I can take this R, Y and B and I connect this R to R, Y to Y, B to B. My line voltages are same, but my phase voltages across the load is not same. So this analysis of three-phase three-wire unbalanced circuit can be done in three ways. The first method is transforming star connected load to delta connected load. So what I will do here, ZR, ZY, ZB, I can change it to, I can transform it to delta, equivalent delta. So as I told in the beginning, my line voltages are same, right? This is R, this is Y, this is B, this is my VRN, capital N, I'll take here N, this is VYN, like this, and this will be VBN. And my line voltages will be same as we have discussed earlier. So Y and B. So my line voltages will be here VRY. This line voltage will be VYB and this line voltage will be VBR. So the equivalent delta impedances, what I will get here, that we can calculate, right, by transforming this star to delta, right? And then after taking this impedances, I can calculate the respective delta currents IRY, IYB and IBR. This I can calculate like this. Sorry, this is R. We can calculate like this, and difference of these two currents like IRY and IBR will give me the line current IR. The difference of the currents like IYB and IR will give me current IY. Similarly, I can get the current IB. This method requires lot of conversion technique and then calculation technique. It takes little longer time to calculate because you need to calculate first the line currents, and based on the difference of the two line currents you can get the, based on the two line currents in the delta you can get the line currents in the R, Y and B respectively. The another method is applying loop method. So I have here ZR, this is ZY and this is ZB. This is my terminal this is terminal R, terminal Y and terminal B. So what I can assume here, this is my voltage, line voltage VRY, and this is my line voltage VYB. So I can assume one loop current here. I can write the loop current here I1 and I can write the loop current here as I2. Writing these two equations, loop current 1 and loop current 2, I can have two simultaneous algebraic equations and then solve these two algebraic equations. You can find I1 and I2, and then based on your I1 and I2 values, your I1 will give you your IR, your difference of the two currents I1 and I2 will give you IY, and difference of, not difference, again I2 current will give you IB. So this is another method to find line currents for the unbalanced load when your neutral is not connected to the supply neutral. Coming to the third method, which is called neutral displacement technique. Normally practitioner use this technique, this method, and this method is also called as neutral displacement technique. So my focus today for this lecture is neutral displacement technique. So I'll take here again the load ZR, ZY and ZB. We'll take here the supply voltage, phase voltages as VRN, capital N. Then I'll take this as VBN, sorry, not BN. I'll just erase this. It is YN. It is YN because this node I am writing here NN, and another my voltage is VBN. Now this capital N, which is the neutral point of the supply, and my neutral point of load, they are not at the same potential level. So we need to find out how much shift these neutrals are having. That technique is called neutral shift technique. So what we will do here, supply voltages are phase voltages are VRN, VYN and VBN. But my load voltages are VRN, VYN and VBN. And I need to find out how much is the displacement between capital N and small n. So what I will do here, I will draw a phasor diagram first. So phasor diagram, this is my VR capital N, this is my VB capital N, and this is my VYN, and this is my VBN. These are my supply voltages, and they maintain the line voltages as RY, VRY. They maintain the line voltage as VYB, and they maintain the line voltage as VBR. Now what I will assume here, this neutral is this neutral is not same as the load neutral. Let me change the current. I'll assume here the neutral point of the load is, let me take this as N. Okay, so this is my VRN, this is my VYN, small n, and this is my VBN. I need to find out what is the difference between this capital N and small n. So for that, what I will assume here, I'll transform this load into the admittance triangle. So for that, I will change this to admittance. All impedances, I will change it to the admittance, like this. So this is my RYB phase, like this, RYB. And this is my ZR I will take as ZY, YR. I'll take this as YR, I'll take this as YY, and I'll take this as YB, where my YR is inverse of ZR, YB is inverse of ZB, and YY is inverse of ZY. If we take the reciprocal of this, we can get YR, YB, and YY. Now, let's suppose I have here IR current, I have here IY current, I have here IB current. So, applying this KCL, apply KCL at node N. Apply KCL at node N. So I have here IR plus IY plus IB equal to 0. Now these currents I can express in terms of load voltages. My load voltages are VRN into YR plus VYN into YY plus VBN YB equal to 0. Alright. Now what we will do here, assuming that my load voltages are VRN in terms of supply voltage Rn minus the shift voltage Nn. Right? So we have seen already, like what I want to tell you, that this shift voltage, there is a displacement voltage, that is VNN is the neutral shift voltage. Neutral shift voltage. Now this neutral shift voltage I will use to write for the load voltages. So this is for the phase R. Phase Y it will be VYN minus VNN. Similarly, VBN equal to VB capital N minus VNN. Now all these equations what we have used, I'll take this equation as equation number 2 and my previous equation I will take this as equation number 1. So I'll substitute equation number 2 into equation number 1. What do we get here? We get VRN minus VNN into YR plus VYN minus VNN into YY plus VBN minus VNN into YB is equal to 0. Right? So we can collect all these things, all YR, YY, YB, where we have the common term here, NN, these are the common things. So I can comfortably write an expression for VNNS, VNNS, VR capital N, YR plus VYN, the multiplier is YY plus YBN, YB divided by sum of YR plus YY plus YB. So we get one expression for neutral shift. This potential is called neutral shift potential. Once we calculate this one, we can go back to the previous circuit. My load voltages are VRN, VYN and VBN. I have the impedances as ZR, ZY and ZB. So I can calculate my line currents here. Line currents can be calculated. IR equal to what will be this? It will be VRN minus VNN by ZR, and IY will be VYN minus VNN by ZY, and IB will be VBN minus VNN by ZY. So this is the simplest method and used by all the practitioner, which is called neutral shift method or neutral displacement technique. So this method is called neutral shift or neutral displacement technique. Somewhere you can also find this technique, which is called as Millman's technique. So that's all for this. Thank you.
Like, share, comment and subscribe VNR Digital Learning Resource YouTube channel.